Alright, so in this video, I'm going to show you how to use LTSpice to simulate circuits using transistors and how to get the IV curves from the transistor. So LTSpice is a free simulation software available online. You can download it from just type LTSpice in Google and you can find out it is here. Download for whatever your operating system is, just use that one. So I already downloaded it and installed it in my laptop for like, I don't know how many years, like more than 10 years. So I don't need to do that. So if you don't have it, please definitely click this link and install it to your computer. It is free and it's very popular and useful. So definitely to download it to a computer if you can, all right? So since I already have it, so I just type LTSpice, press enter. I'm going to see this interface. So here you have all these menus. You can start a schematic by clicking this button, or you can open a simulation file you built previously. So you can open from here. And here's the control panel. You can change the color of the simulation background, the color of the traces in the simulation itself. So we're going to show you how these things are being configured in control panel. It's pretty important. Otherwise, your simulation looks not that professional, looks just not really nice, right? So let's start with the schematic first. So click here. I can have a empty schematic. You are going to probably see a different color background. So that means you haven't, it's a new software and you haven't configured anything in the control panel. So we prefer a white color background and some other properties in the traces of the simulation. So let's just do it here. I'm going to show you how to do that. So click control panel and then come over to here, find out waveforms. So you can change the data trace width. So change it to 3, so which is a little bit thicker than Euro. It looks better. And also cursor width doesn't really matter. You can change the font type, but I didn't change it, doesn't matter to me. And the font size to make it a little bit bigger, I use 14 here, right? And then go to color scheme. I just click this label here. And here's the drop-down menu, right? So go to background first. So if you can change the toolbars, the RGB color code, okay? You can change it when you are looking at it. So definitely black is not really good. So make it to white, apply. And also grade, I just want to get rid no, you can keep the grade as actually, it doesn't matter. If you see that, you have the grade here and you can change it, change the color, but actually just don't change it, it's fine. And then axis, so just use a black color for the axis, which is looks more presentable. It's pretty clear to the people who are reading that curve. And you can also change the color of the traces if you like, but the default color is fine to me, so I don't want to bother myself to do that. So now click OK, and if you want to change the drafting, okay, change the background here. It's going to be drafting options, and you can find out it's going to be here, color scheme, and wires. You can change the color of the wires, or go to background, which is the way you can change the background of here. So change it to white, and also so click apply, and then go to grade. I don't want the gray. I don't like the gray over there because sometimes you make a snapshot, you put in the report, you have a little gray over there, looks just not really professional, okay? So just make the grade to be white. So it's going to be the same color as the background so people won't be able to see that. And click OK. So this is how you can change all these minor things to make your schematic and the plot looks more pretty, right? So now let's see how we can simulate NMOS and PMOS in LTSpice. So the first thing you want to do is you want to open the library. You can open the library from so the shortcut for that is going to be F2. If you press F2, you will see the library. And also there's another, you should be able to find it from the menu here, right? But I never use it, so yeah, you can find out that later, I think, if you want to use a menu, but it's just like some extra, click over there. I usually just don't use it. But I just use F2. You press F2, you can find out here. That's a library. So be careful about that. If you are using a Mac, it can be different, a lot different. So use a Windows machine, a PC is highly recommended. If you do not have it, see any schools or labs nearby does have a PC over there. Otherwise, it's a lot of hassle there if you're using a Mac, because this one initially is designed for PC, right? So you find out the library and then you scroll this to the right and you find out the NMOS. So make sure F2, come back again. It's NMOS 4 terminals. It's not NMOS, okay? Make sure you're using NMOS 4. And you can, by using a single click, left click to place it, and you can keep placing more. However, we only need one. And so if you want to quit this placing mode, you can press escape, the escape key on the keyboard, which is on the top left of the keyboard, ESC, right? Just press it, then you quit this mode. And now I want to delete the extra 3 parts over here. I can press delete on the keyboard, or you can use cut here to cut it, right? And then right click, you can cancel that. Just quit from that mode. And now we have a NMOS already placed here. And now what we should do is we should have a voltage source. Scroll to the right side, you find a voltage and click OK. You place the voltage here for VGS, and another voltage here for VDS, and right click to cancel that. And then grab a ground here and right click, and then you scroll the mouse and press F3 on the keyboard to wire things up together. Ground it, and that's a VGS. Ground it, that's VDS. And so the body is being connected to the ground because that's a P substrate, it's a body contact. You want to just short it to the ground, the lowest potential in the circuit. Right? And now I want to name this guy as VGS, name this guy as VDS. So keep in mind, that's the name of the part, and that's the value of the part. So let's give, I don't know, since we are probably, so for the first curve, we are going to sweep this voltage. So let's just give it 0 volts for now. It doesn't matter because we are going to sweep to a DC sweep. It's going to be a variable. So whatever value you are assigning to that is going to be invalid in the simulation. Doesn't matter. So now we give a 5 volts for VDS, and for you right click the NMOS, we can define the length and width. All right. So let's give 1 micron for the length and 2 micron for the width, and then we click OK. But so the parameter for the length and width is not showing up. So the way to do that is you can show the dimension of the transistor is just point to the transistor in the middle and then control right click, right? And then you just check that box and click OK. So double click to check that box and click OK. Then you can show this parameter over there. And another thing, before you do anything, you want to save this. I'm going to save it on the desktop, and then will let you know why I do that. So I will name it as NMOS, and to desktop, because you need a model file as a TXT file. So this will be available on in Canvas and also on my website. So this one defines all these parameters for the semiconductor fabrication process, and you need to load it in order to let LTSpice to do the simulation. And here, so this model file is from CMOS edu, and because the name is too long, so I changed the name to models.txt, but it's exactly the same stuff. And it is from Dr. Jacob Baker from University of Nevada, Las Vegas. So he has the entire set of tutorials about LTSpice, and so we are just reusing the models and his textbook. And you can go to his website and find out, for example, LTSpice. There are a bunch of resource probably you want to use for to teach yourself how to use it. Okay. So anyway, so we are using the model file from that textbook he wrote. All right, so that's a recommended textbook for you can find out the name of the textbook in the syllabus, and recommend it to buy it, and there are a lot of good stuff in there. So so now we are using, so you can see that they have a model for N1 micron technology NMOS and 1 micron technology PMOS, or some short channel design, 50 nanometer design for NMOS and 50 nanometer design for the PMOS. We're only using the N_1 micron for now. So, and there's one parameter you want to take a look. VTO is a threshold voltage for this NMOS is 0.8 volts. So which means as long as your VGS is larger than 0.8 volts, you can turn on the channel for the NMOS. Okay. So we want to save it in the same directory, which is a desktop over here. So this simulation file can easily find the model file over here. So now what we need to do is I already save it on the desktop, and I need to change the name of that NMOS to N_1 micron, which is 1U. So it knows this is going to use a model defined in here in this model file. And now the next step is to write a simulation code, which is telling LTSpice what to do. The first thing you need to put a dot, include models.txt, right? So to include that model file to load it. So the simulation file knows what are these parameters in the fabrication process. And you want to change the line. So if you just press enter, it's going to, by default, that will pick up OK and close the window. But if you use a control enter, it's going to change the line. So you can type another line here. So we want to do a DC sweep. So which is .dc analysis actually. So DC analysis, so we want to sweep VGS from 0 to 5 volts, okay? And for every 0.1 volt, I want to plot a point in the curve. All right, so I think that's it. It's gonna be, this is good enough for you guys to simulate the first circuit you will in the semester. So let's try it and see what's going to happen. Hopefully it's going to run. All right, so I click the little running man here, and I opened this file. So, but there's nothing here to be plotted because I didn't pick up any output to be plotted in the monitor. So now I can zoom in, and what I'm interested in is actually the IDS. So I will point my mouse cursor here. You can see that if I see this kind of probe with a circle and looks black, so this is a current probe. Okay. If I see something like this is a voltage probe. So what I'm interested in right now is the IDS. So it's a current. So I need a current probe, and I want to click. So see that here is a correct VGS to I curve, and you can see the threshold voltage is pretty close to 0.8 volts. But you can see 1 volt here, but probably it's a little bit less than 1 volt. It's the curve start increase significantly from here. So threshold voltage is close to 0.8 volts. So let's see if I change it to like I don't know, 2 volts or 2 volts, let's say. And I close it, save it and close it. And let's run this simulation again. So that you can see that the threshold voltage just increased to 2 volts, right? So that means our simulation is pretty valid. It's working. All right, let's change it back to 0.8 volts. All right, save, Control S, and then close. Okay, so the first simulation is working, and I'm gonna close it. And everything here for the simulation for the circuit I just drew here, I will attach it underneath, just beside the video. Can be underneath the video or just beside it. I haven't done that so far, but it's gonna be available around that video, this video file. So you know, feel free to check it out and try it by yourself. Try to replicate it. So now PMOS. I'm gonna start a new file. All right. So and actually you can save it first before you move forward. Let's say PMOS and save it to the desktop. You know, the reason is we have the model file in the same directory, so you can directly include that model file. It's able to find it. And we have a blank, you know, empty blank schematic. You want to put parts in there. So press F2, open the library, and then pick up PMOS 4 here and put it here. So there's one thing you want to keep in mind. So here, since you can see that the gate is not in the middle, it's here. So whenever this is closer to this terminal, that means this terminal is actually the source. So what we want to do is we want to flip it, Control R, and then we mirror it, just this one. You know, here is still active in this mode. So you don't actually have to quit this mode. You directly move your mouse to here, then you can mirror it, right? So now it's in a good shape right now, good direction. So here's the source, here's the drain, here's the gate, okay? And we know that the name of the PMOS in the model file is p_1u. Let's change it, and let's change the width to be 2 micron and the length to be 1 micron. You know, it doesn't have to be like that, but usually we just pick up a value that can make it work for this example. And we are not trying to modify and to calculate how much current is going to be flow through the channel by using like what kind of width and length, right? It's not an analog class. We just pick up a value and make it work. That's what we need to do right now. And we have the model set up and we have the width and length defined. So now we need a voltage source. And we get a voltage source. And we need another voltage source for VSD, right? So this one, yeah, let's move it. And let's press F3 on the keyboard and we connect here. So we just formed a VSG. Okay. For VSD, we need this VSD, and we ground D here. Yeah, that looks a little bit odd, but you will be used to that. And connect the body to the highest potential on the circuit. And the body for the PMOS is the NWL. Okay. And again, it's not a microelectronics class. We are not going to dig too deep on that, why we connect that pin to the highest potential, but in the NMOS, we connect that one to the ground. And why is this NWL? Why is not P substrate? Doesn't matter. Just keep in mind, in the PMOS, you always connect the body contact to the highest potential in the circuit. And in the NMOS, you always connect the body contact to the lowest potential in the circuit, right? That's it, okay? You want to keep that consistent in the future. So now let's give so we need to sweep VGS. So we need a VDS to be, for example, 5 volts, and we need a VGS to be, let's just give a value, for example, 0 volts. Since we're going to sweep it, so it doesn't matter what's the value you're going to give to it. And we need to name it a VSG, and we need to name it to VSD, right? The same thing, we click .op and we do include models.txt and control enter to change the line, and we do a .dc analysis, and the voltage source is VSG, and it's going to switch from 0 to 5 volts, and every 0.1 volt is going to plot the point in the circuit, in the curve, right? Put it here, and now let's click the running man, and now we probe to here, so it's going to show the current flow through this channel, and let's do it. All right, so it's pretty much the same thing, but actually the threshold voltage for this VSG is 0.9 volts. So you can see there's a little shift here, okay? And I think that's everything you need to know for this simulation. And another thing I want to show you is, let's go back to the NMOS. And what we just did is a DC sweep for the VGS. So what about the saturation curve for VDS? This is pretty important as well. So the way to do that is I'm gonna change the value here to 5 volts to make that value constant, and we're going to sweep VDS for this time. So let's change that one to VDS. And you don't need to change these things. You just sweep it from 0 to 5 volts, right? Now let's simulate it and look at the current. So it's like that. So that's a VDS curve. That's an IDS curve, but versus VDS. So you have a increase of current in the beginning, but it's going to saturate later on, right? So you need to know that. And you can do the same thing for the PMOS as well to make the similar changes to it. Okay. So that's what you need to know for simulation. Okay. So I think that's it. Just show you all these fundamental operations for this, for how to grab a NMOS and a PMOS to make a simulation work. So hopefully you can practice on your own, and I'm gonna see you in the next video.